we start? It's recorded starts. It's on. On. The recording started? Okay. 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 So we start with what where we left last time. Big statement. Well, so I'll allow me to. So what we have done last time is that we get these matrices, and we have proven that the matrices we get here, like D plus E, is same thing as what we know already as a steady state. Okay. So now, and we also discussed in the tutorial how to calculate these correlation functions. Okay. So one of the things which I want to tell you today is that how to write. This is a process. The whole process you know now, but question is that how to write these matrices or these equations just looking at rate equations instead of writing the details of this, and is there a formula kind of thing, so that you can look at the equation, you can write it how, right? So that is one thing we do. Another thing which I last time which I forgot to do is that do you need, once you have these matrices, that gives you algebra. So the algebra, like like here, like P dq equal to dEd. So there are 4 equations you get here. I will write it here. P dq equal to dEd. This is one equation, and d square. This is d square equal to d square E. So this, and these are the 2 equations, and there is a symmetry, right? Which you just replace d by E. So P eq equal to E dE, and E d square equal to E square d. So these are the 4 equations, and there is a symmetry. The equations are invariant when d goes to E, right? So if you take these equations, you make d goes to E, you get these equations. Okay, so these are invariant under d goes to E. So now, a very simple way to calculate is that what is the magnetization of the system? Okay, so which you calculated earlier, that it is 0. Explicitly you have calculated sigma x t to the power L, whatever, it is 0. Here it is very easy, because you just say that what is magnetization. So if it is +1, if it is d plus, then you have to put 1, and if it is minus, you have to -1, and then you sum it up, right? So that will be d minus E. The operator is d minus E at any site. So it will d minus E t to the power L minus 1 trace of that divided by trace of t to the power L. That has to be SI average at any I, because this dE you can put anywhere. Is it clear?
And T is D plus E.
T is D plus E. Okay, because that is t to the power L will generate all the configurations. So immediately you can see that this will be 0, because if you exchange D and E, this becomes negative. So this equation should be same as when you change D equal to E. So this will be 0 directly. So there is no magnetization is 0. So I will give you so this, what you say is that to get the magnetization equal to 0, you don't need what is the representation of the matrix. Generally, if you know the algebra is sufficient to tell you what is the expectation values without knowing explicitly what the matrices are. Many cases you can do it. I insist that you calculate energy average of the system. What is energy average? So when it is D and E, I just say that it is DD, this plus plus, this is +1, plus EE, this is the operator, minus DE minus ED. Right? That's the operator, because when it is plus minus, you went to -1, energy -1, and of course there is a minus overall. That's the energy of the site, because minus J. Right? So plus plus minus, that's the energy. So this one is minus D minus E whole square. Because D minus E whole square, if you put D minus E, then it is DD, this, EE, this, DE, ED. Okay? So this is D minus E whole square. EDD, they don't commute. So all you have energy expectation equal to trace of D minus E whole square, T to the power L minus 2 divided by trace of T to the power L. I insist that, because if it, the equation is invariant under D goes to E transformation, and if you put D goes to E, this will get a minus sign. So the expectation value has to be 0. That's the only one which you change a minus sign remain invariant. 0 is the only one which you change sign, it remain invariant. Okay? So I insist that don't use the representation of matrices. Use these rules to find out what it is. Okay? Try. So these rules are enough to calculate what is the expectation value of energy. You don't need the representation. So that's the right. I mean, so in some problems, without the representation, you can calculate it. This is something which I wanted to say. Sorry. Yes.
How did we arrive at
D equal to D plus E? T equal to D plus E? Oh no. So partition function, I'm writing it, let us say D trace of D plus, I mean just let us say that what it is. D plus E whole to the power L, which means D plus E, D plus E, D plus E. So this is, there is a trace. So what is the first term? Trace of D, 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 all D. So this is all plus. So there are 2 to the power L terms. Every configuration has some weight, which you have defined. Matrix product says that is the weight. This is just sum over weight of all configurations, equal to sum of weight of all configurations, all 2 to the power L configurations. ठीक है ना? चलो. Okay. So first thing, let us see that how do you arrive at this equation. There will be 8 equations, but some of them are just pair. This one is same as this one, okay, with a minus sign, okay. But you have to write them together, okay. So before we do this, I don't know which one first. Okay, this one first. So what is the matrix? So let us summarize what we have done in matrix product answer. Your P vector equal to DE cross DE cross DE cross DE like that. L terms, okay, and trace of that. That means that it will give you a vector. Each first element is trace of D, 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 D. Next one is D, 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 E. Next one is D, D, E, D. These are the traces written. So this is 2 to the power L dimensional vector. This is your P, okay. And what you have written, achha, by the way, so let me, visually, it will be more appealing if I write it not horizontally, write it vertically. Then the operations become much easier. So for example, A cross B, I will write A cross B like that, this way. You just write it now. So A cross B, a dot product, simple product with C cross D. You know A operates on C, so this is equal to AC BD. So this is visually much nicer, okay. So let us write what is the matrix which we wrote earlier. So what we define is that matrix, like, you know, you have M matrix, so dP by dt equal to MP, and this M matrix equal to summation, this is 2 to the power L matrix, this is summation over I, Ki. And what is Ki? So for example, K1 equal to, no, I think I wrote it Mi. Mi equal to, the first one is K, which is a 8 by 8 matrix, and then cross I, like that. M1, yes. Okay. So I will write the vectors, I will call them x, dE as a vector of matrices, whatever it means. I will call it this way, x cross x cross x cross x. So your probability is x cross x cross x cross x, like that. This is your probability. Actually, x is a good thing. Okay, I call it x, so x. Okay. So this is your probability vector. I will be confused, but x. Okay. So these are x. So this is your probability vector, and trace is there. Of course, trace is there, but imagine that there is a trace is also small written, because I want to write it trace. So this is one vector. So trace of, right? I mean, that is the vector. Same thing, I'm writing it this way, calling it x, 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 I'm writing it this way. So then your matrix M equal to the first one, what you call M1, it will operate on these three. I think it is becoming confusing, so let me call it cross and this. I erase them. Let me call it A. A cross A cross A cross A cross A, like that. So what is your matrix? And there is a trace here. And what is this M? The first element is that this is K. K will operate on three of them. And then I said that cross I, cross I, cross I, like that. So this will operate here, this will operate here, this will operate here, like that, right? So this is not the vector. So the matrix is this plus, first one is I, and then you will operate on these three, cross K, this will operate on three of them. So then the other one, it will go, K will go up to this, and then I, cross I, cross I, like this, plus another one, next one. So this K has positions, like first position, second position, third positions, L positions, and then sum of them, right? So what we write is that, so M is full thing, dot, 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 full thing. And then what is the first term? The first term is just K times A cross A cross A. This K is 8 by 8. This is also 8 by 8. So this is one vector. Full thing is one vector. Cross A, cross A, cross A, like that. K operating on this. And then next one will K operating on next three, next three, next three, next three. So what we wanted to say is that there is M such terms, right? M such terms. We say that each individual terms gives you 0. Because if you want 0, if this is 0, then everything is 0. And you don't have to bother what is this. This one has to be 0. Then automatically the second one will be 0 now, because all you are saying that K times A. So your condition you put K times A cross A cross A equal to 0. And that is K is a matrix, this 8 by 8 matrix. Operating on A cross A is just DE, 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 so the DDD, DDE, like that. That is the condition you use. Is it clear? So all you use is K times this equal to 0. So once K times this equal to 0, the next one is 0, the previous one 0, everything is 0. Is it okay? Right? So K times A equal to 0, which means that K operating on DDD, DDE, trace is there, DED, like the full vector, that is 0. And that is the one which I write it here. This will give you these equations. It's clear, right? Questions here? This is exactly same thing as if you are doing this quantum mechanical class, that the other one, information. So if you have states, like you have S1, right, it can be plus, minus, or whatever. So if you have a Hamiltonian, it is possible that you have a Hamiltonian So let us say 3 spins or maybe L spins. If you have L spins, the spin is a 2 Hilbert space. So you have a vector here, you are calling it plus minus whatever it is. So you have a vector like some let us say it can be plus or minus, let us say plus. I call it S1. S1 can be any vector, cross S2, cross S3, like that. This is the direct product of in the spin space. This is the spin, current spin. And if you have a Hamiltonian, let us say that a Hamiltonian which is H equal to summation over I sigma Z I sigma X I plus 1. I don't know, I'm just writing some Hamiltonian. What does this Hamiltonian do? This means that this Hamiltonian is basically sigma Z cross sigma X cross I cross I cross I. This is first one, I equal to 1. Second term plus I cross sigma Z cross sigma X cross I cross I. This is second term. So all it does is that this one operating on these two, keeping our other things same, plus second two it operates, keeps it same. That is the way the state operates. All I am treating the same kind of Hamiltonian, same treatment, but the elements are not simple vectors, they are vector of matrices. That's the meaning matrix product. So you can call what you do in a spin space, it's a vector product space. All you are doing is a matrix product. So yeah, you can see that this equal to 0, that's all you want, is like finding a ground state of a many-body quantum spin systems. But the interesting part here is that sigma Z, sigma X, it is not that, so instead of this, you can have a Hamiltonian, which is a 4x4 Hamiltonian, which is Hermitian. K is a Hermitian operator, K dagger equal to K. So then what will happen is that instead of these two, all Hermitian operators cannot be can be written as a product of two, direct product of two matrices. Na? So you can have other matrices. So you can have a matrix, general matrix K operating on this, right? And this matrix K is Hermitian, has to be Hermitian because in a quantum mechanical it is Hermitian. All what I'm doing here is that this K is a matrix like this, M, but this is not Hermitian because this element 1, 2, 3, 1, 2, 3, it's not same. It's not a Hermitian matrix. And that's the reason it becomes a little complex, but the algebra and everything is no different. This is no different from what I'm doing in quantum mechanics. Okay? But then, okay, this is clear. So far it's clear. So what we want to do now is that, okay, we'll erase this. And what I wanted to do is that I don't want to put it 0 because one individual thing becoming 0 is not something very useful. Let us say that how else you can generally write this. You will still, under the sum it will cancel, but individual term is not 0. Okay, so initially what did you write? Let me erase that again. Your equations are like K operating on DE or DE cross, okay, let me call DE cross DE cross DE equal to 0. That was this is 8 by 8 matrix, this is the 8 by 8 vector. Of course, trace is there. That is what you are putting it 0. Here there is no trace. You are directly putting it here. Trace was outside, but then because it is all other things remain same and this can be anything, if this matrix operating on this gives a 0 matrix, then of course everything is 0. Right? So that is the way you use it. Clear? So this is the first equation you write. And this, of course, gives you this. So now I will write a general one, how it will cancel. We'll see that how it will cancel. Okay, so what I write is that instead of this, I mean, this is same thing as notation I'm changing. So I also say that K, A cross A equal to 0 in this notation. So instead of doing this, I will write it that in general, this is K times this is D cross DE cross DE cross DE minus DE cross DE cross DE, but I will now put a tilde. I will introduce new matrices. What I do is that K times this equal to this times this. And now I will put a tilde here. No, I'm putting this. This is my demand. I'm saying that if I do this, under the sum, this will be 0. Doesn't matter what K is. Let us see this. Do you see that it is 0? Let us see this. So we just say that, so this is at some place which is I. This is the one where your operation takes place. And then, of course, K is operating on this, but there are in the, I mean, how do I say this? I don't, so before that also there is a DE. There is also a DE here. DE cross DE, operating only this, and after that also some other things are there. Okay? There is also DE, DE there. And total, there are L terms. So now, when it operates on I, you get this one, right? I mean, this one you get at I. So what is the first term you get? So let us write it someplace. DE, first one we leave. Let us operate on DE, and let us say cross DE cross DE. Okay, these three we operate, and we keep some other terms here. DE cross DE. So now, if I operate on these three, I mean particularly here, these three terms will be replaced by these terms. This one I will replace this term. So in terms of, let us, if you write in X, the notation X, so this is X cross, sorry, sorry, I'm sorry, so sorry. I call it A cross A cross A cross A cross A cross A. All I'm writing is that first three thing, when I operate here, this thing will be replaced by A tilde. Now you can drop this symbol you can drop, right? So this is A, so this is equivalent to, let us write it, so this is equivalent to A, and you are operating on these three. So when you operate on these three, this become A tilde A minus A tilde, right? So this will be A, and these three becomes A tilde A minus A tilde. So write A on this operation, I write A tilde A minus A tilde. And then there are other A's. Right? I mean, when K operates on this three, then this is the thing you get.
This only works for periodic boundary conditions, right?
He has already proven it. Okay? So it's 0. Yeah. So it is periodic boundary conditions. Yeah. So this is the first term. Now let us say that you operate on these three. So that will be the second term. What is the second term? Let us write the second term. This is the first term. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have to write, but then first two I don't operate, next three I operate. So the term will be AA plus AA, and next one A A minus A. So do 2 and this 3, 5, and there is one A here. A tilde and A tilde. A tilde A tilde. And what is the next term? I will have another term plus A, and the next 3 will be A minus A, like that. And here it will be tilde here and a tilde here. So now you can see that this one is operating 1, this one is operating 1, and this one is operating 2, and the third one is operating on this 3. Okay, and there are other terms also. 6 times you have to operate, but I just say 3 times I operate. But it will also shift A and A. These 3A also will do this. It will, periodically you have 3 more terms. But you can look at this term. This term is A, 2A, 1 A tilde, and A rest is A. I think I wrote it wrong. Right? 1, 2A and A tilde A. Now this term is, first is 3A, A tilde and 2A. This one is 3A, A tilde and A. This cancels out, right? Do you see that this cancels out? This term here cancels out with this term. If you multiply, this is minus 3A, A tilde and 2A. It is plus, this one is 3A, A tilde and 2A. So they cancels out. Is it clear that cancels out under the sum? And then this one is left, but then this term is 4A, A tilde A, then this is 4A, A tilde A. So this one cancels out with this term. Is it clear now? This is something which is crucial. So if you want more time, I'll leave you here for 3 minutes or 5 minutes, let us say. But let's be clear about it. So all what you have, again, I'll repeat. So this I erase. I just say that what we have is that a state which is represented by A cross A cross A cross A cross A, like that. When my matrix is operating on three sides, like 3 of them, and when it operates, I'm demanding that my matrix K operating on A cross A cross A. This is I'm writing it. So this is A tilde, A tilde A minus A tilde. This is how I'm writing it. Okay? So, in my notation, I'm not using these ones. 6 A's are there. So now I write it's equal to 6 A's. A. So I will first operate on this. So which means that these 3 will be written like that. Should I erase that? I don't know. So if I operate on these 3, so the term will be A tilde A minus A tilde times 3A. This is the first term. Now I say that next I operate on these 3. So this will be A tilde A minus A tilde. This 3 is gone, and next 2 A's I keep it. Next I will erase that, operate on this 3. So this is plus this, plus the next one will be A and A tilde A minus A tilde, only one A left, like that. And then I will operate on this 3, right? So what is happening is that A tilde A tilde, and then 4 A's is, this will cancel with something else. This is A square, A tilde, and 3 A's. A square, A tilde, and 3A. This is 1, 2, 3. So this term cancels with this term. And then similarly, this negative term, 3A, A tilde, 2A. This is 3A, A tilde, 2A. That also cancels out. This is simple.
Where did we get that relationship of A operating on
I'm demanding. I'm asking that, I'm saying that, right? I mean, in my matrix product answers, I had a matrix D and E which I did not know. You had same apprehension at the beginning, saying that, aha, how will it work? Orbital, you are writing some DE. So I don't know what are the DE now. Similarly, I don't know what are D tilde, A tilde now. I introduce new matrices, they are constant matrices, some matrices. I'm trying to say first that the dp by dt equal to 0, which means the stationary state, must be same thing as m times this state has to be 0. If I write individually, locally this condition, then this cancels out. You say that, I know another way to cancel out. Yes, I also know another way. I'll write that. So this I called a cancellation scheme 1. Okay? How else you can write? For 3 side, you can you think of how do you write so that it cancels out? I erase this, is it okay? Actually, some people say that.
I'm sorry, could you please repeat what is the result of this substitution? So we say that K acts on A times A times A in this way. And so what is the result of this?
We'll get to that. First, let us, this is under, if M operates, if I use this condition, M, which is this plus this plus this plus this, which means operating here plus operating here plus operating here plus operating here, this on this will be 0, right? If this condition is satisfied, then it is 0. So I will put this condition here and see whatever happens. Like we'll go there later. But let us use another cancellation scheme just to saying that there are other cancellation schemes. Yes.
Will it still work if we cyclically move the tildes? So
Yeah, no, let us write it. So I am erasing this because, yeah, okay. Okay. So now let us take another state. So K times, you are suggesting something, but write it in equations. So K times A equal to, what do you want to write?
A tilde AA minus A tilde.
Okay, let us write it. A tilde A minus, that will work. No, that is another one, 2 tildes. Okay, 2 tildes also it will work. So you can also say this is another. This will also work, but this is no different from the previous. It is just moving backward. Forward is better. So I will not use this. This is similar. But you can use also 2 tildes. Like so, for example, KAA equal to A tilde. Sorry. A tilde A minus A tilde. A tilde. Will it work? It will work, right? Can you check yourself? So are you getting this point? That this is under the cancel, it will work. So first 3 you replace by this, second 3, so you have A, you start with A, let us say 6 of them. So first 3 you replace by A tilde A minus A tilde, this 3 times A. Now you erase that plus, now this 3. So now I write A tilde A minus A tilde, and rest what is remaining is A, like this. So now you can A, 2A tilde, 3A, A, 2A tilde, 1 and 2 here, that also cancels out. Like they will cancel out. So this, I will also say a cancellation scheme 2. I will try whatever works. A, if I'm writing it everywhere, right? Otherwise, A cross A cross A. So this is tilde minus A cross A cross A. These are tildes. This equation also will work. Yes?
What if I have only 3 schemes?
Then we don't do matrix product answers. Write the 8 by 8 matrix, diagonalize in Mathematica. I mean, I mean, no, I mean, any problem, 3 sides, 8 matrix can be solved exactly. That's not what we are trying. We are looking for a thermodynamic system. I think 16 sides can be solved. Huh.
I'm sorry, could you please explain once again what do we get out of the cancellation of these terms? Did you understand this yet or not?
So this is M and this is P, right? If you put a small trace here, trace is there, I was not writing. This is my matrix M, which is the equation dp by, like, you know, we have equation initially dp by dt equal to mp. That was the equation we started with. This is the M and this is the P. And I want a steady state, mp equal to 0. I want this to be 0. And this one gives me k operating on first 3, k operating on second 3, k operating on 3. That is the way the M is. So I'm writing it k operating on the full thing is k operating on first 3 plus k operating on second 3, third 3, fourth 3, like that. And that has to be 0. And I'm saying that if I write this, then it will be 0 automatically. I have to figure out what are a tilde. I don't know yet. I have to figure out what are they.
Okay, but what happens with the rest of the terms? For example, in the second scheme, there are also 2 terms left, so they don't automatically go to 0.
I mean, because I have not completed it. You complete it, it will be 0. 6 of them you write, it will be 0. It's in a periodic thing, no? All sides. It's not. I mean, how many times you operate on 6? Like, okay. Okay. I did not complete it. A. 1, 2, these 3, and 3, and then this 4, and then, I don't know, 5, I don't know, and then next one 6. I don't know how to do this. These 2. 6. If you write 6 of them, all of them cancels out. The first one also left, like this one, will come out. Under the sum, that will cancel out. Write it like that, it will cancel out. Write it like that, also it will cancel out. But these A tildes are called auxiliary matrices. D is called D tilde, E is called E tilde. So this is a very strange way. When you do not know a solution of for 2 matrices, you now look for another 2. Okay? But you can eventually, let's write the equation. So can you write what it will be? What will be this? If you use this cancellation scheme, this K is this matrix operating on, the vectors are D, D, D. This is like, you know, A cross A is D, 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 E. This is there. I don't have a space here. D, 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 E. This is the matrix on which you operate, D, D, E. And that is the way you have written. First term is minus this into D, D, D plus minus P into D, D, D plus 1 into D, D, E, like that. And now you have to write the right hand side. Right hand side is what? This is it. What is this matrix? The cancellation. So A tilde, let us write it. DE cross D tilde E tilde cross DE minus DE cross DE cross D tilde E tilde. That's the meaning of A tilde A minus A tilde. That's what I write, right? So what is the first term here? D tilde D, D tilde D. So this first term is D, D tilde D minus. From here, D, D, D tilde. So this one, this operating on this thing, first thing, will be this, equal to D, D tilde D minus D, D, D tilde. Right? It's only whatever the element plus, whatever for matrix is, whatever you are writing, plus, plus, plus. So plus, plus tilde, plus, minus, plus, tilde, tilde. Like that. Right? So what will be this? This is DDE. You are writing it for DDE. So this is plus, plus, plus. That's the first thing you are writing for plus, plus, plus. And this is plus, minus, plus, like that. So you are writing for this one is for plus plus minus, sorry, this one you are writing for plus plus minus. Plus plus minus means d d e minus d d e, and then you put tildes. And this one you are writing for third one, d e d. So this is d e d minus d e d. So this is d tilde, e tilde, and d tilde. Can you complete it now? So this one is d, this one is fourth one is. So how do you know for what you are writing? In the equation, whatever you are writing, that is appearing with a minus sign, because that is the diagonal term in the equation. So this you are writing for d e e. So you have to write d e e minus d e e, and then you tilde here and tilde here. That's the equation. Here you are writing e d d equal to e d d minus e d d. So this is d tilde, this is d tilde. So this one is writing for d e d minus. So this is d e d minus d e d, e tilde, d tilde. Are you getting it? So now, yeah. So I will wait for 2 minutes and then we'll look for. Feeling hot. Yeah, it's okay. Anyone who doesn't understand? That's a good way to ask. Huh? Anyone has a question or don't understand what we are doing?
I didn't, so we somehow substituted this constellation scheme into the matrix algebra equations.
Yes, because that is what the equation I'm writing, right? K times A cross A equal to this. I'm just writing that. This is my K matrix operating on a vector which is d d d like this, operating on a vector d d d. This vector is just d d d. I mean d cross e, right? And that's the vector. That each one is giving this. I'm exploiting the other side of the vector. Is it clear? What is this vector? Let us write it again. Let us write the right hand side. Okay. So let us write explicitly d e, that is A, cross d tilde e tilde cross d e minus d e cross d e cross d tilde e tilde, which means a tilde a tilde a minus a tilde a tilde. So let us write in the full matrix form, vector form, what it is. What is the first term? First term here is d tilde d. So I write first term is d tilde d minus, from here you get d tilde. This is d tilde. D tilde minus d tilde. What is the second term? D tilde e. So d tilde e, from here e, and from here I get d e tilde. D e tilde. The next one, like that. So there are 8 elements. The last one is e tilde e minus e tilde. That is what I am writing it here. The last one I will write equal to e tilde e minus e tilde. And this one is EED, I mean EED. So this is e tilde d minus e d tilde. All I am equating is that k times this equal to this. K is this matrix operating on a matrix vector, operating on a vector d d d, d d e, d e d, d e e, and d e d d, e d e, like that. this times that equal to this vector. That's what I'm writing. So the first term is this, which is already I multiplied earlier, and I'm equating, instead of 0, I'm equating this. Still anyone? Now we go to formulas. You know the techniques. So now let us see that given equations, how do we write it? So look at this. So we'll use these equations, and we have a, so yeah. So we'll go to formulas now, right? I mean, how to write it quickly. The technology you know now, and how to write it quickly. Which one I erase? Is it clear? Is it anything which is missed out, or you don't understand at this stage? No, here it doesn't. You have to write 8 equations. So a special case of this, because this, what are these matrices? D and D tilde. Okay, these are auxiliary matrices. That they are not related to the local site. This is some constant matrices, nothing to do with what is there in the site, right? Some arbitrary matrices you are introducing, right? DE are the state vectors, state matrices. These are arbitrary matrices. So you can choose them anything, whatever works, even imaginary numbers. It doesn't matter. If you find a D tilde, E tilde which works for these equations, you are done. So now the task of matrix product in general, but so this is generally true for any dynamics, right? I mean, you can use this cancellation scheme. If this doesn't work, you may try this. You can use your own novel cancellation schemes. So these are the places where you can tune twist. So the original work was only this cancellation scheme. We have used it somewhere else like this, which works. Many other ways one can cancel it, and nice, interesting way you can do this. That's all. So instead of finding DE, we have to now find it DE and D tilde E tilde. In this situation, can I erase this now? Okay. In this situation, a special case, when D tilde equal to D tilde equal to 0 equal to E tilde, is a choice. Then in the previous equation you get back, right? Because, yeah, these are 0 by itself. D tilde can also be scalars. You don't know what they are, right? But question is, why you write like this? I'm saying that what you did at the beginning is that we talk of Ising model for which we knew the steady state. I will now change some dynamics. Let me write it, the dynamics. So the dynamics for the Ising model, we wrote it earlier. So this matrix comes from the fact that you have plus going to minus. This is single spin flip, but it depends on the nearest neighbor. Like it can be plus going to minus. I write it 4 times. Plus going to minus, plus going to minus, plus going to minus. But it can be plus plus, or plus minus, or minus plus, minus minus. And each of them can come back. And all, what is the highest energy is this one, and this one is P. This was the only one P. And from here, if you lose a low energy configuration, that is P. These are the 2 variables which are P, and anything which is not written anything is 1. Right? So how many terms are there? 1, 2, 3, 4, 1, 1, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8 rates are there, and those are appearing here. They are appearing there. So let us say that that is the dynamics. So you want to change the dynamics now, because this should, when somebody tell you that this is the dynamics, and you write these equations looks like that. One solution is D tilde equal E tilde equal to 0, and you could get that solutions. So now let us say that you change the dynamics to anything you like. Then you are completely, right, in a deep water, because you don't know what is the steady state. You don't have a Hamiltonian to a priori guess what is the steady state. You can put your dynamics anything. So let us say that this is P, and this one I call it Q. In the matrix, what do you have? What are the change? What are the change will occur? Can somebody come and tell me which place? Here? Which one will change? All ones. First, third element, this one. This one become Q. Huh?
So P plus Q should be 0. So it should. So this first
P plus Q should be 0. Who said that? Why?
column sum should be.
That will say later. First you write and then you put column sum, right? This is your rate. You can choose anything you like. I will put everything 1, 2, 7, 5, 4, 9, whatever you put. Put whatever you put. Actually, there is a problem. I have given a problem. That question number 10 is this. Okay, so you can put anything. So now the dynamics is well defined, and you can always simulate on one-dimensional system with this dynamics. It will reach a steady state. But what is the weight? What is weight of different configuration? Now you don't know. It's not Ising, nothing. And if you can find a solution just by putting dE, you can put a dE. So now let us say that this one is Q. Where does it appear? First one, here. Third one, that is Q. But then why? Because plus plus gains it, right? Plus plus from minus plus minus with rate 1 it was happening. Now it will happen with rate Q. But plus minus plus also losing with Q. So plus minus plus is also losing with Q. Column sum will be 0 automatically, right? So it will appear in two places. So now what are the change will occur here? I multiply, like here there is a Q. And then in this equation, plus minus plus, plus here, what is that? Plus minus plus, this one. This one also Q. Right? So now, let us write that equation. So now the equations are same or different? Somebody was saying that you don't have 4 equations, you have 8 equations now, right? Because these equations are not same. This will be P d d d minus Q d d. This is a minus sign, right? But this side is different. Hello? This equations I am writing it again. Huh? So what I am writing it from here, minus P, because plus 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 losing with minus P. I am writing it for plus plus plus. Minus P d d d, and then plus plus plus. If I am writing it for plus plus plus, first I write for plus plus plus. I have to write 8 of them. First I write for 8 plus plus plus. So plus 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 losing with P, and gains with from this with rate Q, d e d. And for what I am writing? Plus plus plus. Then I write d d d minus d d d, and tilde I put it properly. This is for plus 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 I write, but in the equation I can write also plus minus plus, right? What is that equation? For plus minus plus, gaining with rate P from this and losing with rate Q. So minus Q plus minus plus, this is minus Q d e d q, that is minus, but it is gaining from plus, so which is plus P times d d d. For what you are writing? Plus minus plus. So you write plus minus plus means d e d minus d e d, and you put your tildes properly. And then similarly, you can write the other equations also. Okay? Yes? But these equations, just one second. So these equations are not, this is just a negative of that, right? But this right hand side, look at the right hand side is different, right? So what you have to write is that for one equation like that, you have to write equations, generally one equation if you want to write, then you start with from here, minus P DDD plus Q DED. Now for DDD, if you are writing for DDD, then it is equal to DDD minus DDD. That is one. And from the other one, whatever you are writing for DDD, the other one is DED. So this is DED but with a minus sign. Minus DED, but tildes placed properly. So that is the equation. When D tilde equal to E tilde equal to 0, I mean 0 equal to 0 is not an equation, it's an identity. So you have these two equations reduces to one equation. In general, you have 8 equations. Okay? So you have 8 equations and you have to solve for 4 matrices. And the matrices are nonlinear. So can you figure out? And the matrices will depend on P, Q, everything. So for example, I will give you exercise because worked hard on this problem here. So I will give you exercise, you do it. Okay. So what I do is that I generally take a rate. This is P plus plus. Let me write it. So forward is P plus plus, backward is Q plus plus. So this one is writing plus minus. So this is P plus minus and this one is Q plus minus. Similarly, this one is P minus plus and this one is Q minus plus. This is Q minus minus, P minus minus, this is Q minus minus. So these are general rates. You understand the rates? So your dynamics, I'm talking of a dynamics, this is not Ising. I don't know what it is. And do I know a solutions? Yes, not always, but we can, I'm asking you to solve it and figure it out. So the problem is that you have you have plus going to minus, this is single spin dynamics, but it depends on spin SS prime here, S and S prime, plus going to minus. The forward rate is P SS prime, the backward rate is Q SS prime. And my definition is that P Q SS prime divided by P SS prime equal to alpha SS prime. So there is alpha plus plus, alpha plus minus, alpha minus minus, alpha minus minus. So the demand is that, so when, so the question is when alpha minus minus, alpha plus plus equal to alpha square, okay, square root of alpha plus plus alpha minus equal to alpha plus minus equal to alpha minus plus. If this is the condition satisfied by the rates, then you have a 2 by 2 solution. Okay, so the question is find out D and E. D tilde and E tilde are constants. So the solution, you write it. I will erase. Can I erase this now? I can erase this. So when this, so that I have a solution so that DE is 2 by 2. Okay, with D tilde equal to E times D, D times D, E tilde equal to E times E. You can take any choice. This is okay. It's a choice. This is so there is a solution exists, but this is not Ising model. Although there is a 2 by 2 matrix, okay. Any 2 by 2 matrix can be thought of, and it's asymmetric. It will be asymmetric matrix. So you will get this DE is something T equal to D plus E. You get D plus E, but this one and this one will be different, and this one look okay. You will get it A, B, C, D in general. Okay. So Ising model plus minus and minus plus, the interactions are same. Okay. So these kind of interactions are now generally kind of being interesting. It's called non-reciprocal interaction. some way plus minus interact differently at minus plus. But this is not too, how to say, too interesting a problem, because any 2 by 2, all 2 by 2 matrices are symmetric. If it is not, you can always make a similarity transformation to make it symmetric, because this one is isospectral to A, B, square root of C, BC, square root of BC, if all of them are positive. Of course, all of them are positive. Okay, so this becomes a symmetry. So eigenvalues of this matrix and this matrix are same, because determinant and traces are same. Okay, so there is a similarity transformation which brings that. And for this, you can write a generalizing Hamiltonian and a Monte Carlo dynamics. So which means that you get a stationary state, whatever you are getting here, through a non-equilibrium dynamics, can also be achieved by some Hamiltonian with equilibrium dynamics. Right? The state is same, Ising state corresponding to this Hamiltonian. What kind of Hamiltonian this is? This is Ising model with a field. Because if you have Ising, no, I mean, I think I'm going far. Yeah, figure it out, yeah. Because Ising model with a field, you have a matrix of this time. This one is different from this, because here it will be plus plus, you get a, here it is plus minus, the field will not contribute, you get a matrix like that. Transfer matrix, all I'm saying is the transfer matrix of Ising model to 1D Ising model with a field looks like this. These two things are different and these two things are same. Without a field, these two are also same. Like e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta, e to the power minus beta. So these two same, these two same. This is without field. With a field, you have something alpha, here minus alpha, like that. So these two things will be different. So if you equate them, you can get an Ising model whose steady state is same thing as the steady state of this. Okay, so at this stage, I'll wait for 2 minutes for a break at some questions, and then I will go to a new problem.
The new matrix is
Huh?
in the diagonal, the new matrix is A.
D,
It's a D.
yeah. AD equal to AD. Trace is AD, this both of them. Determinant is AD minus BC, both of them. So the eigenvalues are same. These are isospectral, yeah. Yes?
Can you uniquely figure out just using D tilde and E tilde?
Yes?
That's
Yeah, yeah, yeah. We'll figure out now in a different problem. This one is because 3 sides it's becoming messy. It's a 8 by 8 matrix we have to handle. Then there are 8 equations, and yeah, it आँखों में दर्द होता है 8 equation handle करने में. We'll just do it 4 equations.
So we need D tildes and E tildes because we remove this detailed balance condition of that.
Yeah, it's a general solutions. You don't want detailed balance. I do, because in arbitrary dynamics you have arbitrary solutions, like, right? Because, right? So the whole point is that now you appreciate Boltzmann for his thing, like, because somebody has told you the steady state is a big help. If I give you only the rate, I ask you what is the steady state, you are in trouble. Particularly it's a big system, 2 to the power L matrix, 2 to the power L by 2 to the power L matrix, it's difficult, even if it's a linear problem. Some matrix into a vector equal to 0, solve it. And the solution is not this easy, and this is one method at least you can try. Any other questions? I will go to the problem, 2-particle problem. Yes? No, we do not know the dimension of D and me. We do not know even there is a solution for this problem or not. As I say, that why I am using these conditions. It's a back calculation, like, you do this, do, and eventually you figure out that, okay, if you want demand forcibly that it has to be 2 by 2, then it has to be this condition. If it is not, then I still do not know what is the steady state. If you write 3, 4, 7, 5, 4, 9, I don't know what is the steady state. It's not that I solve this problem. I solve this problem under this condition. Okay? Okay. Any other questions? So now we will go to a problem which is
So if you change some rates at some arbitrary points, of course the steady state might still satisfy detailed balance, right? So you don't know.
no, you don't know. Yeah. You don't know the detail balance. Yes, you can actually. Yeah.
So So it's possible that you can find, I mean, like you might find a solution this way, but it's possible that that will also satisfy detail.
Yes. So for example, if you keep this as 1 and this one you call it Q, then it's a detailed valence. No? Directly, what happens, the plus plus has a different energies than minus minus. It doesn't matter. So you write a Hamiltonian like that, plus plus has different energy. So you write any Ising Hamiltonian can be written as H equal to e to the power minus beta, not H, T S1 S2 equal to e to the power plus beta, f of S1 S, f of S1 S2, and H equal to minus summation over I f of Si plus 1. You can choose any function. You have a transfer matrix, 2 by 2 transfer matrix. So for plus plus, if you choose P something alpha, minus minus, you have a different energy. You still have a Hamiltonian system, and you have a dynamics, and the dynamics will look like that. This one flipping with a different rate, minus minus flipping with a different rate, and things like that.
In principle, given these rates, you know whether they are going to satisfy detailed balance or not.
Yes. No, if you know the steady state.
No,
I know the rate also you know. Yeah, yeah.
I
Oh,
mean,
yeah.
you don't know the steady state by using this
Yeah.
Kolmogorov
Normally, yeah, conditions you can find out. Yeah.
And then you can, in principle, build the steady state right from there.
Yes, for the right, you know.
But it's like
It's just give.
tedious job, but in principle you can find the steady state.
Only for
when-
equilibrium system. If it
Yeah,
is,
if it is satisfies detailed balance.
yes, then you can find it.
Then you can find out, right? I mean,
Yeah. Yeah, you can find out. Yeah.
Excuse me, so we need the scheme only for like non-equilibrium steady states, because in
For equilibrium, I also said, for Ising model, we calculated it.
Yes, yes. While we are looking for equilibrium steady states, we have detailed balance conditions, and we don't have to have this cancellation scheme. Do you understand this correctly?
You don't have the cancellation. D tilde equal to 0 will work. Yeah.
Okay.
Yeah. But the reverse is not true. It is possible that D tilde is 0, but the system is not still in equilibrium. It just ensures that there is no current. For detailed balance, it is, yeah, one side it is true. If it is detailed balance, this will work. If you know that the rates which you are writing satisfy, right now it is the rates for some Hamiltonian, then you are assured that right hand side 0 will work. Because that is the way, I mean, I'm not doing anything, right? I mean, this equal to 0. That is, each of them is a detailed balance condition. You see, the condition is, if I say that P dq equal to 0 is the detailed balance condition. You see, if I say that dq, P times dq equal to ded times q1. So P times dq equal to ded. That is the detailed balance, yeah. So you're writing the detailed balance condition there. So eventually this has to be 0 for equilibrium. If you know that it is equilibrium, you can set it to be 0. But generally, when I write arbitrarily, you don't know. Okay, any other questions? So now let us try a simple problem, little bit whatever we can, and then we go next to tomorrow. This I don't need any more, I will erase. Okay, so the problem so there are two different kind of particles on a lattice. Okay, so there are A's and there are B's. These are the two different kind of particles. And the dynamics is just A0 going to 0A with rate PQ, B0 going to 0B with rate alpha beta. So there are two kind of particle in a lattice, and the particles move. I don't know, PQ can be anything. So there is a rate at which the particle move forward, backward. So this is a forward moving rate of A particle with P, and forward moving rate of B particle with rate alpha. Backward moving is beta, and this is Q for A. no particles, vacancy. It's just particle move forward. So this is there are, in this problem, there are conservation. There are two particles conserved, right? I mean, number of Na and Nb both conserve. So two conservations law, Na, Nb, or in other words, rho A, rho B. Okay, so these are the conservation laws. So can somebody now tell me what is the dynamics? So the matrices, I call them A, B, and O, I call it 0, I call it O. Then that is easy to write the matrices. Can you write the matrices now? So the first equations, what are the matrices? Can somebody prompt me, because this is what I want. Tell me the matrix equation. Who wants to say this? Somebody. If you don't want to come, just prompt. Why don't you tell me? Matrix will be 2 by 2. But looking at this, can you write the equation in terms of the matrices, A, B's and O? AO is losing. So you write for, how many equations you have to write? 2 sides, 3 different states. So how many equations? No, each side, you have a lattice. Okay, I have not defined this. So you have a lattice, there is a ring, and there are sides. The same thing, 1D ring, and each point you can have a particle or a B particle, or it is vacant. There can be only 3. So there are 3 to the power L configurations now, and you are considering 2 side dynamics, so this can be 3, right? So can you write the equations first? Achha, before that, I think let us, before going that, can you do this only one particle? There is just A0, 1, this is B, let us say drop it. So only A particles are there. This is not there. For the time being, I erase this. Only one conservation law. Now can you write it? What are the equations? How many equations will be there? 4, right? Because you have to write it for, what are they? A0, 0, okay, A0, 0A, AA, 0, 0, right? 0A, A0, AA, 0, 0. So for A0, like particle and then right hand side is vacant, how is it generated? And how it is lost? You have to write them. So A0 loses with probability P. Write that term. You are writing it for A0. So A0 loses with probability P. AO. A0 loses with probability. How is it A0 gained? From OA with red Q. So plus Q, OA. What should you write in the right hand side? You write whatever you are writing, this one, A0. Right? So you write A0 minus A0 and you properly put tildes. Okay? Can you write the next equation for me? 0A. Huh? Q0A or minus Q0A? 0A with red Q loses. Minus Q, 0A. For whatever you are writing, that one has to be minus. That is the point, like, because that one sitting in the diagonal. Minus QA, and how is it gained? AO. Plus P, AO, equal to writing it for 0A. So you write 0A minus 0A with tildes. What about this? AA, nothing happens, right? So left hand side is 0, but right hand side still exists. So 0, nothing, equal to 0, 0, 0, 0, minus 0, 0. So, and so you have to put tildes also, tildes and tildes. This is something people miss out sometimes, so don't miss it out, write everything. And then another 0 equal to, write it somewhere so that 0 and O's are, yeah, I know what 0. So equal to, so what is this? O commutes with O tilde. So I say that O commutes with, this means that O commutes with O tilde. Similarly from other one, A commutes with A tilde. Right, so these are the equations. So now you have 3 equations, no 4 equations of course, minus P AO plus QOA from here, right, minus PAO plus QOA equal to AO minus A tilde O minus A O tilde equal to, from here I get a minus here, minus of O tilde A minus O A tilde, and A tilde must commute. Okay. Now you have to try. So I can keep, I can try, but I look at my note. I forgot. 2 particles. One particle. One particle you don't need anything.
The right hand side.
Huh.
O and O tilde are same. Not commute.
Commute, yes. So what is the thing? So what is the meaning of O tilde? What are the things? These 2 equations, what does it say? With one problem we can try. Let us try. So O tilde is what? O tilde commutes with O. What are the solutions? Constant. If O tilde is a constant, it will work. It's a scalar, then it will work. So if O tilde is a scalar, that is a solution. Other thing, if it's a matrix, what? It's some function of O, right? I mean those are, and linear functions of O's are the good. So those are the things to try. Okay. So now let us say that, take a condition. Let us see that whether it works. Okay. So AO, so A tilde is a constant. I call it A. So if A, then this is O tilde is O. So what about 0? Is it okay? It will work? Let us try with 0. Like if it works, that's the simplest, right? Because you don't have a choice to make. You're just making a choice. So if it A tilde and O tilde equal to 0, then all you have is that the equation reduces to only one equation, QOA equal to PAO. And so AO minus alpha OA equal to 0. Yeah. Will it work? Is there other matrices which satisfy these equations? AO equal to alpha OA. Scalars will not work, right? Yeah. But this one should have a scalar solution. So AO equal to alpha OA equal to AO equal to alpha OA. So it is not that there is no solution. There is a scalar solution when this one is alpha equal to 1. So if you have alpha equal to 1, then AO can be scalars, right? I mean, so when alpha equal to, so when alpha equal to 1, this is what one thing you get. So when alpha equal to 1, then A and O are scalars. A equal to O equal to 1 also would work. Anything would work, but A equal to O equal to 1 equal to work. So if you look at this problem, if this is alpha equal to 1, that is Q equal to P, which means that that is a solution. Okay? Huh? Did I? Huh? Huh? For AO, I'm writing it AO, A tilde O, AO tilde. How? So for two sides, what is the matrix? So do you want me to do? Okay. So let us write this matrix. So if you have A0, so you have A0, 0, 0, 0, A, A0, AA, 0, 0, 0, A, A0, AA. You have to write a master equation which you want to write dp by dt for two sides. dp by dt equal to this Kp and this matrix you have to fill up. Can you fill it up for me? 0, 0 doesn't, so this is all zeros. Okay, and O 0A, from where it can get 0A can come from A0, from here A0 with red Q. There is nothing else. Diagonally I will not put, I'll keep it later. Huh? Minus P. And AO. OA from A0, oh, this is P, sorry. And OA loses with Q, so minus Q, okay? And AO from OA, it is Q, and this one is minus P, 0, 0, 0, 0, 0. So dt, so this is the equation, right? So when you have a state, so you have zeros and A's, so your P, general P equal to AO cross AO cross AO, like that. Now what will happen is that M, so your M matrix, so when you write is that this is your P vector, then dp by dt equal to M times P, okay, and M equal to K, M equal to M1 plus M2 plus M3, like that. And what is M1? M1 is this matrix which is called K, operating on first two sides, right? So this is the matrix which is operate on first two sides. So M1 is now K cross I, like that. This is the matrix which operates on this, and summation over all them. M1 is this, M2 plus, so first two side, next two side, next two side, like that. Is it clear? So now the condition will be this K operating on first two sides will be D tilde A tilde. Let us write this so that in 2 it will be much clearer. Let us write it here. So the matrix is P, what is that matrix? Here the matrix is here. So I will write this matrix times first two sides direct product, which is AA, 0, A0, sorry, AO, OA, so AA and O. This is not the basis on which I write the matrix. I write the other way. So I write 0A. I mean, this matrix will not operate, this is not the matrix in the same basis which I wrote it here. 0A, 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 0A. Then the first one will be 0, 0, like here. And then it will be 0A, then A0, then AA. So then if you first two, is that these two together will be 0, 0, OO, OA, AO, and AA. So what my equation would be now, this matrix, kahan gaya? Here. So my equation will be this matrix operating on, let me write it again. So 0, 0, 0, 0, 0 minus q p0, 0, 0, p0, and 0, 0, 0, 0. This matrix operating on the state 0, 0, 0, a 0, a. So this is k operating on 0, 0a cross 0a. This would be what? My equation is k operating on 0a cross 0a equal to 0a 0a minus 0a 0a properly tilde. Sorry, this is tilde. Okay, so which means this is 0 tilde 0, from here minus 0 0 tilde, from here a tilde, so 0 tilde 0, 0 0 tilde, 0 tilde a minus 0 a tilde. So I will write this here. So this complete thing I will write it here. I multiply and write it here. So this equal to 0 tilde 0 minus 0 0 tilde, and 0 tilde a minus 0 a tilde, then a tilde 0 minus a 0 tilde, and a tilde a minus a tilde. So these are the equations. Now if I multiplied, first thing this times this, it will be just 0 0. So that is what I am getting. So which means that 0 0 tilde minus 0 0 tilde equal to 0, because this operating on this is 0. That is my first equation, this one. Let us say this one minus, so what is that? This one, q times 0a minus q times 0a plus p times a0 minus q times 0a plus p times 0a equal to 0 tilde a minus a tilde 0. So that is this one. Is clear? So this is, I am just saying that, instead of writing the full thing, you can just look at this equation, whatever these equations, from here you can write. Like a0, so that is the way I write it. It's clear, right? Okay, I think the other one you try it next time. Two particle will try it next time. Questions I can take, yeah. So one thing from here what we get is that, a scalar solution, like, alpha equal to 1, you have a scalar solution, that part is clear. So you try, if there, for a simple one, if there are other solutions which you have in general for P not equal to Q, and then we go to two particles. Yeah. Yeah.
Why don't we use two-side dynamics in the previous case? We constructed a k at the 8%.
Who gives you the dynamics is something which you start with, right? In a non-equilibrium systems, you don't start. You start with the dynamics. If you say 3-side, it is 3-side. If you say 4-side, it is 4-side. So in that particular problem, we are looking for a dynamics of Ising model. Okay, for Ising Hamiltonian, there is a metropolis algorithm, and we wanted a spin flip dynamics. And one spin flips, the energy change, to know by flipping a spin how much the energy change, you need to know what is the neighbors. Otherwise, you will not know. Right? So then you have to write the dynamics for the neighbor being plus plus, the neighbor being plus minus, neighbor being minus plus, neighbor being minus minus, and that is the one you write these 8 equations. Okay. Any other question? So just because there are 3 sides, you could use 2 cancellation schemes. 2 different kind of 2 tildes you could use. Here, if you put both of them tilde, then it will not work.
Here we are writing, we are putting a tilde on the first alphabet and then the minus and then the second alphabet. This also needs to be verified, right? Whether it will give us 0 or for all the sides. I mean, how did we write O tilde O?
Yeah, okay, yeah.
I guess you're asking whether it might be possible to find it. You are not guaranteed for any process that you will find such O tilde and it will.
Oh, Aja, yeah. So okay, given a process with that, but the cancel. But once I write that, it will be 0 for sure. But now the last thing is that whether you have matrices will satisfy that. That I don't know. But it will be, if I write it like that this will be 0. If I find, then that is a steady state. And if I know that there is a unique steady state, and if I find one, that is the one.
Is this some version of like similar to pairwise balance? Because like you are not doing pairwise balance.
No, that is right. In the partition function, if you look at this, in the partition function, when you replace, for example, you write it by tilde and replace the tilde by a scalar, then what you are relating is a recursion relation from a system of L to a system of L minus 1. ZL relate to ZL minus 1.
But partition function will be if it's a equilibrium. You are saying, but anyway you define.
No, but I mean, for example, in this problem, doesn't matter what is, right, let us say that even the other problem, let us say A0 equal to this and B0 equal to 0B with alpha beta. I don't know whether I can write, I have a equilibrium Hamiltonian for which this is the dynamics. I don't know.
Even the first you don't.
First also I don't.
Even that you don't have, it's not an equilibrium state.
Yeah. But still, if you find, let us say that I find a D and E, then the probability of each configuration I know, right? Because it is just D plus E, A plus O whole to the power L. This will generate all the states. And trace of that, this one is the partition function because this is sum of all weights, always. So the partition function, I mean, so that will you call it the partition function, but yeah, that is not in the same sense, but it will work. All calculations you can do with this. I mean, partition function for me is just the sum of weights. I'm calling it a partition function. So question is that, if you're saying that partition function is e to the power some f and f is some whether it is, so those are, yeah, there will be, yeah, I don't know. So tomorrow I think one of the problem which we do is just 2 particles in this problem, 2 particles, and we try to figure out that, right, so we'll keep one of them drifting and one of them diffusing. For example, alpha equal to beta and P is not equal to Q. So what will happen is that you have a ring and there are two particles. Let us just take only 2 particles, one A and one B, and there are zeros. And B just diffuses in the system. Okay, so B itself would not generate any current and A drifts, A would generate a current. So if you put both of them together and then you don't allow them to switch, then what will happen is that A will be forced to generate, A has to make a current, but the B cannot diffuse anymore because B has to generate a current. And the current is only one current flows in the system, so J has to be same as JB. Okay, so we'll see how in this non-equilibrium, we can get an exact solution for this problem, and we'll do it tomorrow.
I'm sorry, I don't understand what in such a formulation of dynamics distinguishes the situation on a loop from a situation, for example, on an infinite lattice. Like
Open system. No, then I did not get.
Okay, well, what do we have to do to change it in the dynamics to make it from a problem on a ring to a problem on a like finite lattice?
Yes, so what you have is that, yeah, okay, so that I did not do today, but that I kept it for the last one. But all you have to do is that you have a configuration. So if you have an open system, then something happens here and something happens here, right? So then the endpoints, you can have a matrix like D, D, E, whatever you write, like, for a configuration, but you cannot take a trace anymore. So you have to introduce some vector W, some vector V, which you still do not know. So along with the matrices, the boundaries, you put some vectors, and those vectors has also to be determined along with D. Yeah, I think I would need one.
There these answers will not work. That answer the weight is down minus 4, 8.
No, it will work.
Will that cancel anything?
Yeah, we will find a different kind of. So basically, what will not cancel in between it? You can see that in between it cancels, but the boundary. Yeah. So the boundary will have a different equations. You make it WD, so the boundary will be WD equal to D tilde W. Then everything else has become tilde. The first one has not been, and this W will make it. So that will cancel it. You are getting the point? So similarly, so you get extra equation there. If you have a boundary condition, then you have extra equation there. We can do this, yeah. So for me, let me say a problem, another problem, for just to answer your question. So you have a problem where in dynamics here, it's just 1, 0 goes to 0, 1. It's a lattice, finite size L, and each point you can have 1 and 0, and particle just move forward. And this one corresponds to a, if you call it 1 is D and 0 is E, the dynamics on a ring is just one equation, dE equal to D plus E, if it is on a ring. But if you have a boundary, then you have a W here and you have a V here. First question is that find out that on a ring, this is the only equation. D tilde E tilde equal to constant, D tilde equal to minus E tilde equal to 1. This will work on a ring. Okay? But then this will, so if you put a boundary condition extra, then this problem will reduce to additional conditions like W tilde D equal to W here, and so the problem is that let us say alpha red particle enters here. So if you have a minus 1 E here, then it becomes D. So WE equal to 1 by alpha E, 1 by alpha W, something like that. Extra equations will come like that. And from this side, dV, particle goes out with red beta. So that is will give you dV equal to 1 by beta V. Okay, so you have three equations. One is dE equal to D plus E, and this one. You have to solve them together. Do you find matrices D and E such that their sum is same as their product, and left eigenvector of one of them is supplied, right eigenvector of another one is also supplied. So eigenvector, one of the eigenvalue is given. For D, one eigenvalue is specified, and E, one eigenvalue is specified. Given this, can you find matrices whose sum is same as their product? We'll come there, and so this problem we will not be able to do probably fully, but two particles we'll do tomorrow. I think one other, yeah. So the one more class I think I want.